Hey everyone. Firstly, thank you to my friends at Passive Safety UK for the footage of the 2022 Passive Safety Crash Demonstration Day that you've just seen. Look out for links to find out more about them below. We'll be looking at some more of these clips as part of our introduction to passive safety and its implications for ITS infrastructure. So make sure you've got your safety belt on. We may be in for a bumpy ride. I'm Alistair, and this is ITS Now. So, what is passive safety? I think that was an advertisement for a brand of beer. Not quite sure what point they were trying to make, but I think it conveys our concept really well. This is a video of a test carried out at TRL on a 114mm diameter steel post with a 100 kph vehicle impact. The devastating effect, the forces exerted on the occupants, the incursion into the passenger cell would result in near certain fatalities. This test was witnessed by David Milne, who worked at the Highways Agency as was, and felt that the risks associated with the hazard presented by ubiquitous roadside structures was unacceptable. This led to him writing passive safety into the design manual for roads and bridges, which led to the eventual development of the associated requirements over the years. This is what happens to a car when it hits a steel pole at 100 kilometers an hour. But surely we can protect these by using safety fence, can't we? Unfortunately, the consequences of hitting a rigid structure, even when protected by a vehicle restraint system, can be devastating. This example shows the outcome of a fatal incident where a vehicle went over the vehicle restraint system, resulting in it being trapped in the concrete posts on this advanced destination sign. A passively safe signpost. This example is an aluminium lattice post. And here we have an example of a passively safe signpost after an accident. You can see this is broken off at the ground. And this is the car which caused that previous incident. The damage appears to be limited to the front bumper area. Examples of damage sustained by cars hitting comparable traditional, that's the blue car on the left, and crash friendly, the white car on the right, poles. If this had been a real incident, the forces exerted on passengers in the blue car would have been significant. And with the damage to the passenger cell of the vehicle, it is unlikely anyone would have survived. The white car, by contrast, was actually driven by a stunt driver into a passive pole, and apart from the crumple zone on the front, he retained use of steering and braking. In the event of an accident, it has been found that the severity of injury sustained by vehicle occupants can be greatly diminished by the use of roadside support structures that are designed to detach or yield in a predetermined manner under vehicle impact. Many people I've talked to about the need to consider passively safe design solutions have cited concerns about these flying off when hit and causing secondary accidents. However, I think this example of a car striking a traditional wide-base steel pole really demonstrates how unsafe these products can be. Just watch the huge energy transfer that occurs from the car to the pole, and look at how it becomes a really dangerous projectile, particularly considering its speed and mass. It would inflict very serious injuries to anyone in the way. A passive product should, by contrast, experience very little energy transfer, and these are usually much lighter than steel products. So what happens when roadside structures with electrical installations are struck? In this example of a passively safe traffic signal pole, the signal head was shed from the pole and can just be seen on the ground adjacent to the pole. So whether the structure is designed to break away on impact or not, it can be seen that the integrity of electrical installations in roadside structures are typically compromised, leaving potentially live conductors exposed. Irrespective of the type of structure, when poles are struck by an errant vehicle, items of electrical installations, such as luminaires, signal heads, CCTV cameras, etc., are often shed from the pole on impact due to their mass. Cables are also commonly damaged near to the ground level in all types of posts, irrespective of if they are designed to break away or yield on impact, and damage can also occur in traditional steel products, which can also fail when struck. For whatever reason these incidents occur, it affects drivers of all backgrounds, on roads of all types, and importantly to note, not just high-speed roads. In addition to drivers of errant vehicles, passengers, passers-by, and members of the emergency services can also be involved in these events. It could also affect highway authority representatives, designers, suppliers, installers, and maintainers of equipment in the event of a fatality or serious injury. If the police decide to investigate an incident because they feel that a failing in an equipment installation played a contributory factor to a fatality or serious injury. So basically, it doesn't matter how good an installation is that you've designed, someone will find an inventive way to try to destroy it. In this crash demonstration of the 2022 National Passive Safety Crash Demonstration Day, a 114mm diameter FSP composite signal pole mounted in a Riveton retention socket along with a Charles Endirect impact electrical isolation device was shown to successfully operate when struck by this car, with very little deceleration and damage to the vehicle. In this example, a larger 200mm diameter pole product aluminium pole supporting a Wescotec vehicle activated sign with both a photovoltaic panel and a wind turbine, again mounted in a Riveton retention socket. Again, the post performed to expectation. The damage to the car can clearly be seen to be confined to the front crumple zone, without any damage to the windscreen, roof, or passenger cell. The presence of the PV panel and turbine didn't appear to have any impact on the pole's performance. And you can see the equipment is basically in and around the location where it was installed. We're also showing an example of a signal pole from the event a few years ago. This is an interesting example tested at a slower speed and it shows the pole yielding under the car and the traffic signal head being shed on impact. Again, only the front crumple zone was damaged. Even the glass sunroof survived unscathed. And lastly, I couldn't conclude without showing what would be the driver's view of a similar impact event. You can see some damage to the front bonnet. So again, it's damage is occurring to the crumple zone. So the safety features in the car are actually working as they should.
Please remember to click on the like and subscribe to keep updated on ITS now.
For ITS practitioners, the implications of electrical circuits and passively safe roadside structures is a vitally important factor that requires consideration. Because of this, I wrote the guidance document, which was published in 2021 by the Institute of Highway Engineers. The necessity for the IHE Passive Safety Electrical Guide has been heightened due to the changes in the current version of BSEN 12767 standard, which includes the removal of electrical requirements from the UK National Annex to bring this into line with other European countries. Due to the complexity of cable arrangements found in typical intelligent transport systems installations, such as traffic signals, this omission poses potential problems to practitioners undertaking the design, specification, or management of ITS equipment. It is not unusual to have a mix of cable types with multiple cores for numerous electrical circuits, mixed in with data, communications, even coax video feeds, and separate power supply cables for ancillary units within the roadside equipment. The electrical items were primarily included in the previous 2007 edition of the standard because of concerns that the presence of cables within the structures could adversely affect the failure mode of the crash-friendly item in the event of a vehicle strike, resulting in the tethering of poles and columns. Because of this, the advice concentrated on the use of snatch plugs, which physically separate when the pole is struck. The electrical isolation was seen as a secondary benefit. The annex also stated that electrical circuit protective devices could be used to provide electrical isolation. This, though, was written before commercially available impact or tilt switch systems became available, and therefore did not explicitly consider their use. The IHE Passive Safety Electrical Guide therefore examines why impact electrical isolation, or IEI, systems should be considered when designing any roadside ITS installation, including those mounted on passively safe or traditional structures. It looks at why an IEI system may be required in addition to standard electrical protective devices, the different types of IEI solutions which are commercially available in the UK, and how the selection of the type of pole and column should influence the IEI technology used. It should be noted that for street lighting columns and illuminated signs, reference should be made of the separate guidance produced by the Institution of Lighting Professionals. So what are the available IEI design solutions? The first of these are snatch plugs. These are commonly supplied as molded cable assemblies and can be highly successful when correctly installed at ground level within the column. However, these will not work effectively if they are incorrectly located, such as in an adjacent access chamber or too high up within a pole. The cable assemblies also need to be tightly tethered within the duct network and in the pole to guarantee separation at the earliest point of an incident. Because of the required location, they can be difficult to install and to undertake periodic inspections of. Impact or tilt sensors. These systems provide effective electrical isolation in the event of a vehicle strike. These can be costly if a large number of isolators are required to protect multiple cores. They work by installing a sensor on the column, which, when struck or if disconnected, cause circuit breakers located in an adjacent cabinet or chamber enclosure to operate, providing electrical isolation of the installation. Circuit protection device. Although these devices will be required to provide electrical protection for circuits in accordance with BS 7671 requirements for electrical installations, or wiring regs as they're commonly referred to, they cannot guarantee electrical isolation is achieved in the event of a vehicle striking a pole. This is because these types of devices are designed to provide protection from electrical malfunctions and would require a short circuit to operate the device. The requirement is to operate within 0.4 of a second of a vehicle strike, but with degrading installations or poorly specified circuits, this may not be achieved. How do I achieve the correct IEI solution for a particular installation? In this example of a passive traffic signal pole, which was struck by a car, you can see that it was folded flat from the top of the retention socket it was installed in. The steel wire armored cable in the pole was crimped so tightly in the folded section that it could not be extracted without cutting it free. It is thought, therefore, that it would be highly unlikely that a snatch plug would have successfully separated in this type of scenario. Therefore, if this installation was relying on that type of isolation solution, it probably would not have worked. The Institute of Lighting Professionals has recommended that for non-separating installations, the appropriate solution is an electrical isolation system, which is triggered by either an impact or tilt sensor on each structure that incorporates an electrical installation. These may also be used as an appropriate solution for separating installations, although there is scope in these to use snatch plugs instead. We should also consider the use of electrical isolation systems for traditional non-passive poles and columns. Use a risk assessment-based procedure to document the decision-making process, irrespective of the type of isolation system used. We'll look at that in a minute. So a key element that needs to be undertaken is an effective designer's risk assessment. It is recommended that as part of the duties for clients, designers, and contractors under the Construction Designer Management Regulations, or CDM for short, a risk assessment-based procedure to document the decision-making process for all equipment specified as part of an ITS installation is undertaken, irrespective of the type of structure or isolation system used. Along with safe designs and communicating any remaining significant risks, the IHE guidance document fulfills the three fundamentals for the principles of prevention, recognized as being essential for the achievement of successful design risk management in construction projects. Designer risk assessments should consider a wide range of issues, and as with any meaningful assessment process, should use the ERIC principles to seek to eliminate risks, and only when this is not achievable, to reduce risks or to inform parties about any residual significant risks. This will then allow any control measures to be established prior to them being required. Consideration will need to be given to issues that will be faced during the whole life cycle of the facility, covering the construction and installation, use, maintenance, and even decommissioning phases. Each roadside ITS installation project will face very different issues because of the vast array of equipment types and the individual characteristics for each installation site. Examples of items to be considered are included in the guidance document. But what about extra low voltage installations? Over the years, many have queried the need to include impact electrical isolation features for passively safe technology installations, which only include extra low voltage or ELV circuits. This is because ELV systems are at a safe level below 50 volts RMS, so that they do not present an electric shock hazard. However, there are some residual risks associated with these. They could still pose a risk of causing sparks, which theoretically could ignite a fire in the event of a vehicle having a ruptured fuel line or tank after hitting a pole. In addition, because emergency services will not necessarily know if an installation is ELV or not, the lack of an IEI system in place might delay the response to an incident. As ELV installations become more prevalent across highway deployments, emerging technologies such as distributed traffic signal architectures are starting to see the integration of impact sensors into equipment. This trend should be encouraged, but consideration of how these facilities are implemented will need to ensure that they are suitable for the failure mode of the passively safe structure they are used with. The design process for a project using ELV installations should include a designer's risk assessment. This is really a critical element of the whole design phase for a project, and there's no escaping how relevant this becomes, particularly in a few years' time if there is an incident that occurs on a site. So whether or not IEI features are included, you need to document that decision-making process so there is documentation that it has been considered and it just wasn't not considered or forgotten about at the time. It should be noted that ELV traffic signal controller cabinets and the electrical feeder pillars they are connected to contain low voltage. So LV mains electrical supplies are at 230 volts AC. The conversion to extra low voltage, ELV, takes place within the traffic signal controller, where the external circuits make use of supplies at less than 50 volts RMS. Although it is possible to obtain cabinets that are rated as passively safe, because the mains electrical supplies and the possible presence of maintenance personnel at the traffic signal controller cabinet, it is recommended to locate these in a protected location behind a vehicle restraint system or in a position and at a sufficient distance away from the carriageway so that it is highly unlikely to be struck by an errant vehicle. So how do you get your copy of the guidance document? It's freely available. Download it from the IHE website. The address is on the screen, the ihe.org/passiveITS, or find the publication section on www.itsnow.org. Anyone involved in the design, specification, maintenance and management of roadside ITS infrastructure needs to understand the issues which passive safety poses. Here in the UK, there is a common misconception that this is only relevant to roads with a speed limit of 50 miles an hour or more. However, the British standard mentioned in this film, BSEN 12767, shows that it is a consideration for all roads. Therefore, as part of the design process, you need to undertake the designer's risk assessment and include it in the project design file, whether you decide to include or exclude an IEI system. Make sure to look at the IHE Passive Safety Electrical Guidance document for more information. This is free to download. Have a look at the publication section of the newly updated ITS Now website, which is itsnow.org, to get your copy. Please don't forget to subscribe to our channel. Thank you to everyone who's done so far. We'll have more ITS content for you, so see you next time.